Hello everyone, welcome. In this video, I'm going to talk about different methods that you can use to optimize your own portfolio. I will discuss their advantages and limitations. By the end of this video, I will also talk about how I apply them to my own trading. So hopefully this video is helpful to you. Let's get started. When I first started trading, for a while, I was just using the equal weights method. So what does this method mean? It's very simple. It means that if I have N strategies, I'll be just giving the same equity to each of my strategy. But after a while, I felt like I could definitely do better than this, because at that time, the strategy that I was trading, some of them were quite correlated with each other. So it doesn't seem to be very smart, right? To just give them the equal weights. I could definitely do something smarter than that. So let's try to formulate our problem, right? So say that you're standing here. This is now. You want a set of weights that you can use in the future, let's say tomorrow, to trade on, such that you can get very good return. So at this moment, what information do you have? What data do you have? You have your historical returns. That could be either from, say, a back test, or could just from your historical records. Based on those returns, you can get some statistics. So you know the mean, the standard deviation of each of your strategies, and you also know the covariance or correlation metrics. The general idea is that we want to maximize our Sharpe ratio. So Sharpe ratio is simply the return of your portfolio minus the risk-free return divided by the standard deviation of your portfolio. It is very intuitive, right? So giving the same amount of risk, I want to maximize my return as much as possible. So typically we want this number to be relatively big in your sample test. And hopefully this pattern will continue in the future so that we can also get a very good Sharpe ratio in the future. Now we have clear definition of our problem. We can proceed with the first method, that is the mean variance method. So this method was first proposed by a guy called Harry Markowitz. Because of mean variance, Harry Markowitz has won the Nobel Prize, I think, in 1990 in economics. So this is considered as one of the classics when it comes to portfolio optimization. So what does this method do, basically? The idea behind the mean variance method is actually very straightforward. So what we want is that we want to maximize our return while minimizing our risk. So it boils down to solve this optimization problem where we want to maximize this utility function. So this utility function is just return minus some level of some sort of risk. And then you can solve for weights, and then this is the outcome. So we can also try to draw this problem out, right? I bet you have seen this graph before. This is the famous efficient frontier. So what does this graph tell us? So you can consider each red dot on this graph as a possibility of weight allocation. And you see that eventually you have this curve where that means for a given risk, what is the best return that you could possibly get with that risk. Given this graph, I would imagine that, for instance, my equal weights allocation will be somewhere over here. That is definitely not on this curve. Now it seems like we have already solved our problem. We just need to maximize this utility function and then solve this formula for W, and then we're kind of done. But is it it? Is it that simple? Well, when it comes to mean variance methods, there are certain limitations we need to be careful with. The first limitation is estimation error. Mean variance method assumes our returns to be normally distributed. But as we know, normal distribution is often not a good assumption when it comes to financial data. Many times we can observe fat tails. So maybe in this case, t-distribution is a better approximation. The distribution could also be skewed, and kurtosis could also play a role in here. So simply assuming our returns are normally distributed could bring in a lot of estimation error. Another factor is more related with covariance metrics. In order to get our weight W, we need to invert this matrix, which is often a big source for estimation error. The second limitation is actually more intuitive. So in order to use these methods, we are expected to have a lot of data. Just imagine a simple case, right? So you have two strategies. The first strategy is you hold bond, and then the second strategy is you hold QQQ. And you decide to use 3 months of data to apply this mean variance method. For some reason, during the past 3 months, QQQ was doing very badly. And very naturally, these methods will give low weights to QQQ because it's only saw past 3 months of data. To overcome that, you need to sort of feed in more data to get a better estimation for your returns. And some research have shown that you will need at least 6,000 points for 50 strategies and 3,000 points for 25 strategies. Now I want to quickly share a paper. That is the famous 1/n paper. So the two limitations, among a lot of other things, are well discussed in this paper. If you're interested, definitely have a read. So what does this paper try to do? This paper tried to compare the out-of-sample performance of the 1/n, basically the equal weights methods, against the vanilla mean variance methods and some mean variance methods with a lot of variations. So you see you have different numbers of methods here that are all mean variance methods with some kind of variation, so hopefully have better results. So for instance, you have one method that uses some approach to reduce the estimation error. You also have some other one that has some certain constraints on the portfolio, for instance saying that you cannot short sell, etc., etc. The author also used a lot of data sets, as you can see over here, to apply the methods on. And then the results or the conclusion of the paper showed that actually none of these methods could beat 1/n or the equal weights method consistently. None of them. Okay, so how do we proceed from here? So far we have seen two methods, the equal weights method and then the mean variance methods. The mean variance methods looked very promising at the beginning, but then we see that in reality it is not very optimal. So what can we do? You see, the equal weights requires no estimation, right? It is simply 1/n. Mean variance, you have to use a lot of estimation. You have to come up with a lot of estimation yourself. What about we settle something in the middle? What if we only look at risk? The risk parity methods only cares about your covariance matrix. It doesn't care about the return at all. So compared with the equal weight portfolio, it looks like something like this. So say that this pie chart represents different variants of your strategies in your equal weight portfolio, and then what your equal weight portfolio does is just to simply give it 20% to each strategy. On contrary, the risk parity portfolio, knowing that each strategy has variance like this, will try to make sure every strategy will eventually contribute to the portfolio the same amount of risk. And then by having this in the back of your head, you try to then allocate the weights. This seems to make a lot of sense, right? Compared with mean variance methods, we expect this method to be a lot more stable in the sense of outputting weights, because variance are in general more comparable with each other, so you wouldn't expect to come up with extreme weights a lot of the times. On the other hand, with the mean variance methods, if one strategy has very high return, that strategy will have a very dominant effect on the overall weighting. So, okay, risk parity seems to be doing very well. However, during the calculation process, it still requires you to invert the covariance matrix. So some estimation, is still there. Knowing this, can we do better? Now I want to introduce another another method that is called the hierarchy risk parity. This is a very interesting one. Hierarchical risk parity brings in graph theory to cope with this problem. So it first tries to create a dendrogram of strategies. So what it essentially does is that it's try to basically cluster things together. So in this example, you can see that the methods try to cluster strategy 1 and 8 together, and with 9, so on and so forth. You can also think of it, for instance, strategy 1 and 8 could be just 2 US stocks, and then this part could be UK stocks, and then eventually the right hand side of this diagram is just stocks, and then the left hand side could just be bonds, and then you have UK bonds, US bonds, so on and so forth. So it tries to cluster things by looking at their correlation. And after we have this graph, we can then work on our new covariance matrix. So you see, compared with before, the after covariance matrix is a lot more clustered. And by having this new information, we can then put on weights to the strategies using a top-down method. And then eventually every strategy is given to a weight. While I was reading this paper and learning about this method, it kind of reminded me of this menu clustering that I read from this book. So what does this menu clustering mean? Is just like you can essentially put things together, group things together, by expecting that they will behave very similarly to each other. So for instance, you can start with bond and stock. You give 50-50 to each of them, and then within bond, you give 50-50 to UK and US bonds. Similarly for stock, so on and so forth. And you compare those two things. Like you would expect that you will get similar results, right, if you use this method. So I think it's generally a good idea to, after you use this method, try to see if they actually intuitively make sense to you. Do you expect the clustering to make sense at all? I think it's a good exercise here in general. And just a side note, this book, while talking about menu clustering, also give you a little bit tips on how you can tweak your weights. For instance, you give 50-50 to US and UK stocks, and then maybe US stock has a better Sharpe ratio, and then you can increase the weight a little bit higher. That you could hope that you can get a better results by doing so. So if you want to know more about it, you can read more into it. But the idea, right, behind the clustering should be the same. We have talked about 4 different kinds of methods. Just want to mention one thing. So with hierarchical risk parity, there's no need to inverse the covariance matrix. So you can think of it as a way that you also get less estimation error compared with both risk parity and mean variance. It's just a thing just to want to mention. Okay, so then it's time for the last method for today. That is the inverse volatility. So as the name suggests, it only cares about the volatility of the strategies. It does not care about covariance metrics at all. So it uses less information, but somehow making it more robust. And then the calculation of this is very straightforward. It's simply 1 over sigma, and then you can just balance that out for all the strategies. Okay, now I want to talk about my experience when applying these methods to my own trading system. As I mentioned earlier, I started to use equal weights. Till this day, I still find it a very useful method to optimize your portfolio. And every time I run any kind of optimization analysis, I use equal weights as a benchmark. And with respect to inverse volatility, risk parity, and hierarchical risk parity, I have been experiencing good performance with them. On the other hand, mean variance, I don't recommend that much. So with my own experience, what I typically find is that mean variance methods likes to give me very extreme weights. So I tried different kinds of modifications to sort of fix this. So for instance, I've tried to add more constraint to my optimization, or try to use a different distribution to model my returns. For instance, I've tried to use T distribution, skew T, etc., etc., but that all didn't seem to work very well. Typically, the results, the out of sample performance, sometimes it is good, and sometimes it is not as good. So it is not very consistent, and potentially because of the different kind of optimization constraint that I added, um, I'm also kind of sometimes getting very weird looking efficient frontier. Um, but I definitely think mean variance is it's a good method to try it with your own data. You can understand how it actually works and then see the result yourself. I think it's a very valuable thing to do. In practice, equal weights and inverse volatility requires no optimization, while the other methods does need optimization. So this is something to keep in mind. Mm, Also, the computational complexity also increases, let's say, from equal weights to inverse volatility to risk parity to hierarchical risk parity. If that's your concern, also keep that in mind. Um, um, about inverse volatility, I want to mention that you have to be careful when your n is relatively small and then there is some high correlations among your strategies. So that could lead to extreme weights or that you definitely do not really want. And also another way to try to stabilize your covariance metrics a bit better is to use the shrinkage method. Um, this it's basically an idea to kind of reduce the extreme values in your covariance metrics, so hopefully reduce the estimation error in general. And then, as I mentioned earlier, for hierarchical risk parity, it's a good thing to compare it with your own beliefs. Like, what do you think things should be clustered together? It's a good second check. In general, I would suggest that when you do optimization, try to use equal weights as your starting weights, and then you go from there. If you want to implement any of the methods mentioned today, you can look into these two Python libraries. So I've used them before, and then I think it's very easy to use. So feel free to look into it. To end today's video, I want to finish off with a fun anecdote. So I read this story from a blog post. I'll also link the blog below. So Harry Markowitz, the guy who invented mean variance, what kind of methods of portfolio optimization did he use eventually, right? So apparently he used a equal weight method for his own retirement or pension per portfolio. So here I quote, I thought, if the stock market goes way up and I'm not in, I'll feel stupid. And if it goes way down and I'm in it, I'll feel stupid. So I went 50-50. So here you go, a fun anecdote to finish today's session. I hope you find this useful, and then I'll see you next time.